Hi everyone. To help myself study probability, I'm going to go over the canonical machine learning problem proposed by my professor in lecture. So let's get started. We're going to assume that a coin flips with a probability p of heads, and p is a uniform random variable that goes from 0 to 1. After flipping 10 times, the result is 10 heads. So what is our expected value of p given that we came up 10 heads? So we're going to start with the definition of the expected value of a conditional probability, which is just this here. We're going to integrate over 0 to 1 because p can only go between 0 and 1. That's the definition of probability. That's the probability density function of p given that we landed 10 heads. I'm going to integrate with respect to dp. So we know p here, we know our bounds, but we do not know the value of this yet. So we are going to evaluate that first. This is a conditional probability density function. So we can rewrite this as f of p given p and landing 10 heads over probability of the event that we have 10 heads. This is again just the definition of conditional probability, and we're going to use that definition again in a different way. So I want to imagine the numerator written as f of p, 10 heads, and p. So we just changed the order, which is fine because this is an and. I'm going to rewrite this now as f of p, or f sub p, 10 heads, given that p is equal to p multiplied by the probability density function f of p. So in the space that p is equal to p, which is this density here, what are the chances that we have 10 heads? That's all we're saying. And we're going to condition this bottom probability on the value of p. Since it's a continuous random variable, we're going to integrate from 0 to 1 of p are 10 heads, given that p is equal to p times probability density, and integrate with respect to dp. So we got that going for us, which is nice. We're going to use the question's assumptions to help us evaluate what's going on here. So we got this here, f sub p of 10 heads given p is p. If the probability of landing a head is p, and we did it 10 times, then this whole probability, or this probability density, is just equal to p to the, it's just equal to p to the 10th, because we did it 10 times. And the probability density here, let me just highlight that. Probability density here is the space that p can equal to p. Since it's uniform from 0 to 1, and we are basically taking the space that p can equal p, we're just going to realize that that is equal to 1 as well. It's uniform from 0 to 1. If you integrate from negative to infinity to positive infinity of any probability density function, you will get 1 by definition. So we got that here, and if you notice, these two terms are actually the same. The only difference is that there's an integral wrapped around the bottom one. So we can write that in here, times 1 with respect to p. And then after some simplifying, we get p to the 10th over p to the 11 over 11? Is that right? I think so. Evaluated from 0 to 1. So p to the 10 over 1 over 11, because, that's just the way it is. That ends up being 11p to the 10. Unfortunately, we're not done. We still have to go over expected value, which is equal to this here We're going to write the definition down again. P times FP given 10 heads, little p dp. But this time we know that this is equal to that, so we're going to sub that in. 0 to 1, p times 11 p 10 dp. We're going to take the 11 out because it's just a constant. We're going to integrate with p to 11 with respect to dp, which is equal to 11 p 12 over 12 evaluated from 0 to 1. And since it's evaluated from 0 to 1, it means nothing. P goes away. P just, yeah. This is our updated value, and this is the expected value of the probability after flipping the coin 10 times and seeing 10 heads, given that we expected it to be a uniform random variable from 0 to 1. Does that make sense? I don't know. Thanks. Bye.